Hello everyone, I am Alok Srivastava from Indian Institute of Technology, Bombay, India. I am a PhD scholar working under Professor Chandra Yerramalli and Professor Aparna Singh. I am here to present a part of my work on effect of graphene coating of carbon fibers on fracture of unidirectional laminates. This presentation is structured as follows. I will begin with the introduction, then I will move on to the materials and methods. Thirdly, I will focus on to the results, and I will end with the conclusions. So carbon fiber laminates are made up of carbon fiber, fabric and the mixture of resin and hardener. The interface between the matrix such as epoxy and the reinforcing phase such as carbon fibers plays a decisive role in determination of mechanical properties of the composites. The problem is illustrated in the schematics of the fiber epoxy junction failure mechanism. After applying the load in the fiber axial direction, it can fail in two ways. The one is along the fiber matrix interface where post-failure neat carbon fibers can be seen easily. The second is due to the rough carbon fiber surface and the some reinforcement. The failure happens away from the carbon fiber which lead to the cohesive failure. Now there are challenges in making these kind of laminates. First one is the insufficient interfacial adhesion due to inert carbon fiber surface and low mechanical interlocking. Second is the reinforcement of nanofillers like graphene nanoplatelets through mixing it into the epoxy resin, which causes the high viscosity of the final mixture. And the third one is the distribution of non-homogeneous GNPs in the mixture. So to overcome these challenges, the objective of the work drawn from these motivations, how to include the nanofillers easily so that it will improve the interfacial interactions between the fibers and the epoxy. I have started with the unidirectional carbon fibers, in which the toes consisting 3000 filament of 7 micrometer diameter each, and the graphene nanoplatelets was procured in powder form, which has larger surface area and the number of layers is 2 to 4. Also, a resin hardener system Epofine 1564 composed of bisphenol A diglycerol ether based resin and the fine hard 3486, which is low viscosity polyethylamine hardener, are used. Now let's move on to the major steps involved into the experiments. The GNPs were ultrasonicated in ethanol with the help of probe sonication to obtain the GNP ethanol suspension. Then the fabrics were coated from both sides alternatively, and the 8 fabrics were spray coated for each set of laminate. Further, the 8 fabrics of each condition laminate were stacked together, and vacuum assisted resin transfer molding technique was used to manufacture the laminates, in which the vacuum assisted infusion of epoxy hardener mixture was done to the stacked fabric and kept it for the curing cycle. The pristine laminate was made up of no GNP addition, and the 0.2 weight% and 0.4 weight% concentration of GNP with respect to the total fabric weight were used to manufacture the 0.2 GNP and 0.4 GNP laminates. After the laminate manufacturing, the static tensile test was carried out as per the ASTM standard, and the specimen is shown over here. The tabbing was done to the grip section of the specimen at the both sides, and the specimen was 150 mm of total length, 25 mm width, and 1.7 mm thickness. Now before moving to the tensile test results, first we will look at the characteristics of the interface, which is characterized by scanning electron microscopy, and the linear elemental mapping of carbon fiber laminates was done by energy dispersive X-ray spectroscopy. A gradual decrease of carbon elements towards the epoxy evidences the formation of interface between the epoxy and the fiber. This gradual change in carbon element with respect to the position measured for 8 different scans for each condition. The average length of the interface for each laminate is plotted in this figure. The average thickness of the interface is highest in case of 0.4 GNP laminate. This increment of the interface thickness is due to the presence of GNPs, which can be attributed to their carbonaceous nature. Now let's move on to the tensile test results of the tabbed specimens. The 0.4 GNP laminate and 0.2 GNP laminate shows 15% and 4% improvement in tensile strength compared to the pristine laminate. This can be attributed to the larger gradient interface and adhesion between the carbon fiber and the epoxy in 0.4 GNP laminates. Also, the Young's modulus of 0.4 GNP shows 10% improvement compared to the pristine and zero point 0.2 GNP laminates. This can be ascribed to the stiffening effect of the rigid GNPs in the gradient interface. In figure B, there is no substantial change in the strain at maximum tensile strength, that is the failure strength of the laminate, with the increase in GNP weight percent. This is ascribed to the fact that the strain of the unidirectional laminates mainly governed by the tensile strain of the fibers due to the major load acting onto the fibers. Now the fractographs of the failed specimens were observed under SEM. Figure A shows cross-sectional fracture surface of the pristine laminate, which indicate the larger debonding gap between the fiber and the epoxy. 0.2 GNP laminate in figure B also shows similar but smaller debonding gaps compared to the pristine laminate. However, in 0.4 GNP laminate, there are closely packed fiber epoxy fracture surface and the debonding gaps are fairly negligible compared to the former laminates. The observation made in 0.4 GNP laminate in figure C is in agreement with the strong interfacial adhesion between the carbon fiber and the epoxy. Likewise, among a longitudinal fracture surface in figure D, E and F, 0.4 GNP laminate shows the largest amount of epoxy adhered onto the fibers. The presence of GNPs in 0.2 GNP laminate in figure G can be seen, which are adhered with the epoxy. Apparently, GNPs in 0.4 GNP laminate in figure H is not similar to the 0.2 GNP, and the flakes of the GNPs of different sizes can be seen, and a strong pull-out of epoxy from the peripheral region of GNP particle can be seen. The pull-out phenomena of the epoxy is ascribed to its higher mechanical interlocking with GNPs, and this resulted in higher tensile strength and modulus of the 0.4 GNP laminates. This brings to the end of my presentation. First, we looked at the formation of larger interface in GNP added laminates, which implies enhanced interfacial interaction of GNPs with fibers and epoxy. And we saw that GNP added laminate showed higher Young's modulus as well as tensile strength compared to the pristine laminates. Also, there were larger debonding gaps between fiber and epoxy when no GNPs were added. Finally, GNPs were found to be adhered along with the epoxy and fibers in GNP added laminates. Based on above remarks, we can conclude that the spray coating of GNPs on unidirectional carbon fibers strengthened the interface between carbon fiber and matrix. I would like to thank my supervisors, Professor Aparna Singh and Professor Chandra Yerramalli. Also met Fact2 for providing me the platform to present my work, and finally the IIT Bombay. Thank you for your attention. You can find me at alok_s@iitb.ac.in.